Welcome to today's session. In this video, we'll be solving problem number 62, unique paths. This is a fascinating problem that explores how to calculate the number of unique paths a robot can take to reach the bottom right corner of a grid, starting from the top left corner, while only moving down or right. We'll break down the problem step by step and examine different approaches to solving it. Let's dive in. In the unique paths problem, we have a robot starting at the top left corner of an MXN grid, which is labeled as position 1, 1. The robot is tasked with reaching the bottom right corner of the grid, denoted as MN. However, the robot can only move in two directions, either down or to the right. Given these constraints, the goal is to determine how many unique paths the robot can take to complete this journey. The input to the problem consists of two integers, m and n, where m represents the number of rows in the grid, and n represents the number of columns. Both m and n lie within the range of 1 to 100. The output will be a single integer that represents the total number of unique paths from the top left to the bottom right corner. For example, if m equals 3 and n equals 7, the grid has 3 rows and 7 columns, and we need to calculate the total number of distinct ways the robot can travel within this grid while following the movement rules. In the first example, where m is 3 and n is 7, the output is 28. This means there are 28 unique paths the robot can take to move from the top left to the bottom right corner. One way to calculate this is through combinatorics or dynamic programming. For instance, one possible unique path could involve the robot moving right 6 times and down 2 times in some order to reach the destination. Now, in the second example, where m is 3 and n is 2, the output is 3. In this case, the grid is narrower, so there are fewer routes available. The robot can take 3 distinct paths, moving down twice and then right once, moving down once, then right, and then down again, or moving right first and then down twice. Each of these paths satisfies the movement constraints. In the third example, we have m equal to 7 and n equal to 3. Interestingly, the output here is also 28. This is because the dimensions of the grid are simply swapped compared to the first example, which makes the problem symmetric. The robot has the same number of unique ways to navigate from the top left to the bottom right corner, as the movement rules remain unchanged. These examples illustrate how the grid's dimensions directly affect the number of unique paths, and they highlight the importance of finding an efficient way to compute these values, especially for larger grids. Finally, there are a few important constraints and edge cases to consider. First, both m and n must be between 1 and 100. This ensures the grid size is manageable, but the number of unique paths can still grow very large, up to a maximum of 10 to the power of 9. For edge cases, if the grid is a single cell, such as when m and n are both 1, the only unique path is for the robot to stay in place, resulting in an output of 1. Similarly, if the grid is a single row or a single column, the robot can only move in one direction, either right or down, so the number of unique paths is also 1. For very large grids, such as 100 by 100, it's critical to use an efficient algorithm to compute the result without running into performance issues or exceeding memory limits. These constraints and edge cases emphasize the need for a solution that balances correctness and efficiency. To tackle the problem of finding unique paths, let's start by considering a basic brute force approach using recursive backtracking. The intuition here is simple: since the robot can only move down or right, we can explore all possible paths by making recursive calls at each step, one to move down and another to move right. The base case occurs when the robot reaches the boundary of the grid, either the last row or the last column. However, the drawback of this approach is its computational inefficiency. The time complexity is exponential, approximately 2m plus n, because each cell spawns 2 recursive calls. This leads to a lot of redundant computations for overlapping subproblems. Additionally, it uses m plus n space for the recursion stack. To address this inefficiency, we can optimize the approach using recursion with memoization. By storing the results of subproblems in a 2D memoization table, we avoid redundant calculations. This reduces both the time and space complexity to m*n, as each cell is computed only once. However, while this method is much faster than brute force, it still requires extra space for the memoization table, which we can optimize further with additional techniques. Building on the idea of optimization, we can shift to a more iterative approach using dynamic programming with tabulation. Instead of recursion, we construct a 2D DP table where each cell represents the number of unique paths to that point. The recurrence relation for this is straightforward. The number of paths to cell I, j, is the sum of the paths from the cell directly above it and the cell to its left, or dp I, j, equals dp I1, j, plus dp I, j1. To initialize the table, we set the first row and the first column to 1, because there's only one way to reach those cells, either by moving exclusively right or exclusively down. At the end of this process, the bottom right cell of the table, dp m1 n1, holds the total number of unique paths. This method has a time complexity of O, m*n, and a space complexity of O, m*n, due to the 2D table. While this approach is efficient, the memory usage can still be reduced. By observing that we only need values from the previous row to compute the current row, we can further optimize the space complexity. Using a 1D array to store just the current row's results allows us to maintain the same recurrence relation while reducing the space complexity to O, n. This space-optimized dynamic programming approach is ideal for handling larger grids efficiently. Among the approaches we've discussed, the space-optimized dynamic programming method stands out as the most efficient solution for this problem. The key insight here is that the problem can be reduced to computing the number of unique paths using only two types of moves, down and right, and the recurrence relation dp I, j equals dp I1, j plus dp I, j1 captures this beautifully. By realizing that only the previous row is needed to compute the current one, we eliminate the need for a full 2D table and use a single 1D array instead. This approach was chosen because it achieves the best balance between time and space efficiency. While it has the same time complexity as the 2D DP approach, O, m*n, it significantly reduces the memory requirement to O, n, making it particularly well suited for larger grids. The trade-off is that this method can be slightly harder for beginners to grasp due to the abstraction of rows, but the efficiency gains make it the optimal choice. Overall, this strategy ensures we solve the problem in the most resource-efficient way possible, with both time and space complexity optimized. To solve the problem of finding all unique paths a robot can take to move from the top left corner to the bottom right corner of an MXN grid, we can start with a brute force approach using recursive backtracking. First, we define the base case. The base case occurs when the robot reaches the bottom right corner, which is the cell at position M1, N1. At this point, we know that a valid path has been completed, so we return 1 to indicate that this path contributes to the total number of unique paths. Next, we explore the possible movements of the robot. From any cell, I, j, the robot can move either right to I, j plus 1, or down to I plus 1, j. For each of these options, we make a recursive call to determine the number of paths from the new position. However, we also need to ensure that the robot stays within the bounds of the grid. If the robot moves out of bounds, meaning that I is greater than or equal to m or j is greater than or equal to n, we terminate that particular recursive path and return 0, as it does not contribute to the total number of unique paths. After exploring the possible movements, we combine the results for each cell. Specifically, the total number of paths from a given cell is the sum of the paths from the cell to the right and the cell below. This sum is then returned to the caller. To initiate the entire process, we start the recursion at the top left corner of the grid, which is cell 0, 0, and compute the total number of paths recursively. Now, while this brute force approach is straightforward and explores all possible paths, it is highly inefficient. The main reason for this inefficiency is that it recalculates the number of paths for the same cells multiple times, as it does not store the results of subproblems. This leads to an exponential time complexity of O, 2 m plus n, in the worst case, where each cell spawns 2 recursive calls. Additionally, the space complexity is O, m plus n, which accounts for the maximum depth of the recursion stack in a grid of size mxn. The recursion itself inherently uses a call stack to keep track of the paths being explored, while the grid is logically represented through indices rather than an explicit matrix. When analyzing edge cases, the behavior of the algorithm becomes clearer. For example, in a 1x1 grid, there is exactly one path available since no movement is required. Similarly, for grids that are either a single row or a single column, there is only one possible path because the robot can only move in one direction. However, as the grid size grows larger, the brute force approach becomes increasingly computationally expensive due to its exponential growth and recursive calls. To address these inefficiencies, we can consider optimizations such as memoization or dynamic programming. Memoization involves storing the results of previously solved subproblems, which eliminates the need to recalculate the number of paths for the same cells multiple times. Dynamic programming, on the other hand, uses a 2D table to iteratively compute the number of paths for each cell in the grid. To better understand the brute force approach, we can review its implementation. The recursive function starts by checking the base case. If the robot has reached the bottom right corner, it returns 1. If the robot moves out of bounds, it returns 0. Otherwise, the function recursively calculates the number of paths by moving right and down, and then sums these results to determine the total number of unique paths. Let's walk through an example to see how the brute force approach works. Suppose the grid is 2 times 2, meaning m equals 2 and n equals 2. The robot starts at the top left corner, which is cell 0, 0. From here, it has 2 options. It can move right to cell 0, 1, or down to cell 1, 0. If the robot moves to 0, 1, it has only one option from there, to move down to the bottom right corner, which is cell 1, 1. Similarly, if the robot moves to 1, 0, it has only one option from there, to move right to the bottom right corner. In total, there are 2 unique paths for the robot to reach its destination. While this example is small and manageable, it highlights the inefficiencies of the brute force approach, as the number of recursive calls grows exponentially with the size of the grid. This is why optimizations, such as memoization or dynamic programming, are critical for solving this problem efficiently in larger grids. This code uses dynamic programming to solve the problem of finding unique paths in an MXN grid. The robot can only move right or down, starting from the top left corner and ending at the bottom right corner. First, a 2D list, DP, is created to represent the grid, initialized with 1s. Each cell DP, I, J, is used to store the number of unique paths to reach that cell. By default, the first row and first column are filled with 1s because there is only one way to reach any cell in the first row, only moving right, or the first column, only moving down. The nested loops iterate through the grid starting from cell 1, 1. For each cell DP, I, J, the number of unique paths is calculated as the sum of paths from the cell above it, DP, I1, J, and the cell to its left, DP, I, J1. This is because the robot can only move from these 2 directions. Finally, the value at the bottom right corner of the grid, DP, M1, N1, is returned. This value represents the total number of unique paths from the start to the end of the grid. This solution has a time complexity of O, M*n, because we iterate through every cell in the grid once, and a space complexity of O, M*n, for the DP table. This is the Java implementation of the unique paths problem. The logic mirrors the Python solution by using a dynamic programming approach with a 2D array. The table is initialized with base cases where the first row and first column are set to 1. Subsequent cells are filled using the relationship DP, I, J equals DP, I1, J, plus DP, I, J1. The final result is stored in DP, M1, N1. Key differences include Java's strict type declarations and array initialization. To solve the problem of finding unique paths in a 3x2 grid, we start by initializing a dynamic programming table, or DP table, with dimensions 3 rows by 2 columns. Each cell in this table represents the number of unique ways to reach that cell in the grid. Initially, all cells are set to 1 because there is exactly one way to reach any cell in the first row or the first column, either by moving only right or only down. The DP table at this stage looks like this: 1, 1, 1, 1, 1, 1. Next, we fill the DP table using the relationship that each cell's value is the sum of the cell directly above it and the cell directly to its left. This approach ensures that we account for all possible paths to each cell in the grid. Now, let's start filling in the values for the DP table. For the cell at row 1, column 1, we calculate DP 1, 1 as the sum of the cell above it, DP 0, 1, and the cell to its left, DP 1, 0. This gives us 1 plus 1 equals 2, so we update DP 1, 1 to 2. The updated DP table becomes 1, 1, 1, 2, 1, 1. Next, for the cell at row 2, column 1, we calculate dp2, 1 as dp1, 1 plus dp2, 0, which equals 2 plus 1 equals 3. The dp table is updated again to 1, 1, 1, 2, 1, 3. Finally, the bottom right cell, which is dp2, 1, contains the total number of unique paths in the grid, 3. Let's now consider a slightly larger grid, a 3x3 grid, where both m and n are 3. As before, we start by initializing a dp table with all cells set to 1, since there's only one way to reach any cell in the first row or first column. The initial dp table looks like this: 1, 1, 1, 1, 1, 1, 1, 1, 1. Using the same approach, we calculate the number of unique paths to each cell starting from row 1, column 1. For this cell, dp1, 1 is the sum of dp0, 1 and dp1, 0, which equals 1 plus 1 equals 2. Next, we calculate the value for the cell at row 1, column 2. Here, dp1, 2 is the sum of dp0, 2 and dp1, 1, which equals 1 plus 2 equals 3. This updates the dp table to 1, 1, 1, 1, 2, 3, 1, 1, 1. Moving to row 2, column 1, we calculate dp2, 1 as dp1, 1 plus dp2, 0, which equals 2 plus 1 equals 3. Finally, for the bottom right cell, dp2, 2, we compute dp2, 2 as dp1, 2 plus dp2, 1, which equals 3 plus 3 equals 6. The updated dp table is 1, 1, 1, 1, 2, 3, 1, 3, 6. The value in the bottom right cell, dp2, 2, represents the total number of unique paths in the grid, 6. For our final example, let's look at a smaller 2x2 grid where both m and n are 2. As usual, we start by initializing the dp table. All cells are set to 1 initially, as there's only one way to reach any cell in the first row or first column. The initial dp table looks like this: 1, 1, 1, 1. Using the same logic, we calculate the values for the remaining cells. For the cell at row 1, column 1, dp1, 1 is computed as the sum of dp0, 1 and dp1, 0, which equals 1 plus 1 equals 2. This updates the dp table to 1, 1, 1, 2. Finally, the value in the bottom right cell of the dp table, dp1, 1, represents the total number of unique paths in the 2x2 grid. In this case, that value is 2. Thus, there are 2 unique paths to travel from the top left corner to the bottom right corner of the grid. To analyze the time complexity of the solution, we start with the initialization of the dp table. This table has dimensions mxn, so setting all m*n cells to their initial value of 1 takes m*n time. Once the table is initialized, we move on to filling it. The nested loops iterate through the rows and columns starting from index 1, because the first row and column are already initialized to 1. For each cell, we compute its value by adding the values from the cell directly above and the cell directly to the left. Since this computation is a constant time operation, O1, and we update M1, N1 cells in total, this step also takes about M*n time. Finally, accessing the result stored in dp M1, N1 is a simple constant time operation, O1. Now, when we combine the time complexities of all these steps, we get the total time complexity of the solution. Initializing the dp table requires M*n, filling the table takes M*n, and accessing the result is O1. Therefore, the overall time complexity is M*n. For the space complexity, the primary consideration is the storage of the dp table. Since it is a 2D list with dimensions mxn, and each entry occupies a constant amount of space, the total space usage for the table is M*n. Additionally, the solution uses a few auxiliary variables, such as loop counters, which require only O1 space. These variables do not significantly affect the overall space complexity. When we combine these elements, the total space complexity is M*n, dominated by the dp table. To put this into perspective, let's compare this dynamic programming approach to a brute force solution. In a naive recursive method, we would explore all possible paths from the top left to the bottom right corner. At each cell, we would recursively calculate paths by moving either right or down, leading to an exponential number of recursive calls. This results in a time complexity of O(2)m plus n, due to the branching at every step. The space complexity of this approach, however, is O(m plus n), determined by the depth of the recursion stack. In contrast, the dynamic programming solution is far more efficient, with a time complexity of O(m*n) and a space complexity of O(m*n). There's also a further optimization that reduces the space complexity to O(n), by using only a single row to store results, as we only need the previous row's values at any step. However, this optimization does not impact the time complexity, which remains O(m*n). The mathematical reasoning for the O(m*n) time complexity in the dynamic programming approach is straightforward. Each cell in the table, dp, I, j, is computed exactly once, and there are m*n cells in total. As a result, the number of operations is directly proportional to the size of the table, confirming a time complexity of O(m*n). Similarly, the space complexity is determined by the storage requirement of the dp table. Since the table contains m*n entries, and no other significant storage is used, the space complexity is also O(m*n). This combination of time and space efficiency makes the dynamic programming method highly effective for solving the unique paths problem. When solving the unique paths problem, there are some common mistakes to watch out for. One major issue is confusing the base cases in recursion. If you forget to terminate the recursion when the robot reaches the bottom right corner of the grid, your code can fall into infinite recursion or result in a stack overflow. To prevent this, always include an explicit check for that condition. Another frequent mistake is neglecting to optimize overlapping subproblems. Since grid-based problems often involve repeated calculations, failing to use memoization or dynamic programming can lead to significant inefficiencies, especially for larger grids, as the time complexity can grow exponentially. Additionally, edge cases like grids with only one row, one column, or even zero dimensions are easy to overlook. Always ensure your solution handles these gracefully. Variations with obstacles also require special attention. If you don't properly validate moves or account for blocked cells, your path count could be incorrect. Lastly, be cautious about assuming non-negative dimensions for the grid. If the dimensions happen to be zero, your code might throw runtime errors. By proactively addressing these issues, you'll avoid many common pitfalls. Now, let's talk about some valuable insights for interviews. Recognizing common patterns in grid-related problems is crucial. Many of these problems involve similar structures, such as moving down or right, counting paths, or avoiding obstacles. Identifying these patterns early can help you quickly apply the correct solution. For path counting problems like unique paths, dynamic programming is often the most efficient approach. Mastering how to construct and populate a dp table is a key skill to focus on. Space optimization is another important technique. If the problem only requires tracking the current and previous rows or columns, you can reduce memory usage by implementing a rolling array instead of storing an entire dp table. During interviews, it's also essential to clarify assumptions upfront, such as the size of the grid, whether obstacles are present, and any movement restrictions. This ensures you're solving the right problem. Finally, it's worth noting that the skills you develop for this problem are applicable to related challenges, like unique paths 2, which includes obstacles, or minimum path sum, where you focus on minimizing the total sum. There's also unique paths 3, which introduces additional constraints like visiting all cells exactly once. Practicing these related problems can deepen your understanding of grid-based algorithms. To wrap up, here are some key insights to keep in mind. For smaller grids, recursion is a practical way to explore all possible paths. However, as the grid size increases, switching to dynamic programming becomes essential for efficiency. Pre-computing values, such as using a cumulative sum table, can be a powerful optimization when dealing with additional constraints in path-related problems. It's also helpful to recognize that many grid-based challenges build on fundamental algorithms like depth-first search, breadth-first search, or backtracking. Strengthening your skills with these foundational techniques will give you the confidence to tackle more complex variations. By combining these strategies, you'll be well prepared to solve a wide variety of grid-related problems effectively. Great job! To wrap up, we reviewed how to solve the unique paths problem using dynamic programming, which is efficient and scales well. We also highlighted some key takeaways, such as recognizing optimal substructure and leveraging combinatorics when applicable. Thanks for following along. Don't forget to like, subscribe, and stay tuned for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!